Humans cannot realistically travel billions of miles into space, so we send spacecraft instead. And one of the most reliable of all spacecraft is NASA's Voyager 1, which is now billions of miles deep into space. However, the faithful craft is now giving scientists reasons to worry, as it has been recently sending strange signals from its current location. Is something wrong with the Voyager 1, or is it doing its job by sending serious warning signals? Join us as we deep dive into Voyager 1's seriously strange signals from 23 billion kilometers away. Modern humans have achieved far more than our ancestors could have imagined. For example, billions of humans observed the moon for millennia without the faintest idea that we could ever set foot on it. However, thanks to amazing inventions from the untiring labors of talented scientists and engineers, that achievement is under our belt. And we are even venturing further into space with companies like SpaceX and NASA both targeting missions to Mars. While the purposes of their missions differ, landing on Mars will significantly expand our reach in deep space as a human race. However, there is a limit to what human space travelers can endure. And there are so many other places in the universe that we would like to investigate many phenomena to try to understand, but they will take us billions of miles away from the only planet we comfortably call home. This is where space probes come in. They are our eyes where we can never hope to reach with our current level of technology. And one such eye that has remained faithful in deep space for decades is the Voyager 1, half of the famous Voyager pair of space probes. When it comes to the time to rank humans' most outstanding achievements, it would simply be impossible not to put the Voyager missions among the highest. In terms of scientific returns on investments, few projects would come close to the Voyagers. Voyager 1 has the distinction of being the first spacecraft to leave the solar system and travel into interstellar space. The probe launched in September 1977, about 2 weeks after its twin Voyager 2, and is more than 14.6 billion miles or 23.5 billion kilometers away from Earth, making it the planet's farthest spacecraft. The spacecraft is forever moving away from us, and fast. According to NASA's Jet Propulsion Laboratory, Voyager 1 is currently traveling through space at 38,000 miles per hour or 17 kilometers per second. The fact is that nobody could have predicted how important Voyager 1 would still be 45 years later when it launched a mission to explore the outer planets of our solar system. The probe has outlasted expectations and continues to transmit data about its journeys back to Earth. The spacecraft notched its biggest record when it entered interstellar space in August 2012, nearly 35 years after it began its journey. However, the discovery was not made public until 2013, when scientists had time to review the data returned by Voyager 1. Voyager 1 was the second of the twin spacecrafts to be launched, but it was the first to race between Jupiter and Saturn. For a generation, the images returned by Voyager 1 have been used in school books and by many media outlets. The spacecraft also carries a special record called the Golden Record, which is designed to transport voices and music from Earth into space in hopes there would be aliens sentient enough to detect and be interested in it. These images were compiled by a committee led by astronomer Carl Sagan. They are housed in gold-plated copper discs that are engraved in the style of a vinyl record album. A portion of the disc contains audio information such as music, greetings in 55 different languages, including some that are very obscure or long extinct, and nature sounds. The discs also include 122 images encoded as vibrations on the disc with decoding instructions. Several symbols depict the method of playing back the record on the cover plate of each. The image decoding instructions are revealed, describing the image start signal, the image aspect ratio, and a reproduction of the first image so the aliens can see if they got it right. A star map that clearly shows the Earth's location completes the picture. If the discs ever get played, the alien listeners will be treated to traditional music from various cultures, such as Native American chants, Scottish bagpipes, and African ritual music. It also has a greatest hits collection of classical music. The most recent songs are Chuck Berry's Johnny Be Good,
Go, Johnny, go, go! Go, Johnny, go!
and a jazz number by Louis Armstrong. Granted, the world has moved on from what it was like in the 70s. Hey, we now have rap music and reality TV, but it's nice to have a piece of us so far out there in space. Besides, NASA did something cool by including a way for aliens to detect how long the probe has been in space if they're intelligent enough and know what half-life is all about. They can examine the uranium-238 fragment attached to the main bus near the record for isotope ratios. Interestingly, some worried that any hostile aliens who discovered the Voyager disk would have a map that would lead them directly to Earth. While that may appear scary at the surface level, the Voyagers will spend tens of thousands of years in interstellar space before they reach another star, so that situation isn't urgent at all. If the disks are ever discovered, it may be in the far future when humans may no longer exist. However, one humbling thing about the Voyagers is that they will outlast us in the universe, even long after they have stopped working or transmitting. With no atmosphere in space, they will never corrode, and there is little for them to crash into in interstellar space. One of the most notable achievements of the Voyager 1 was the Grand Tour, and it was due to one unusual feature. The Voyager missions took advantage of a rare alignment of the outer planets that occurs once every 176 years. This alignment enables spacecraft to slingshot from one planet to the next, making the best use of their limited fuel. NASA had planned to send 2 probes past Jupiter, Saturn, and Pluto, as well as 2 other probes past Jupiter, Uranus, and Neptune. However, budgetary constraints forced NASA to scale back its plans, but the 2 Voyager spacecraft still accomplished a lot. Voyager 2 flew by Jupiter, Saturn, Uranus, and Neptune, while Voyager 1 stayed close to Jupiter and Saturn. Voyager 1 almost didn't get off the ground at its launch, as its rockets came within 3.5 seconds of running out of fuel. However, the probe made it to space safely and raced ahead of its twin after launch, passing beyond the main asteroid belt between Mars and Jupiter before Voyager 2. The first images of Jupiter were returned to Earth by Voyager 1 in April 1978, when the probe was 165 million miles or 266 million kilometers away, to loud jubilations all over the world. And in March 1979, Voyager 1 discovered a thin ring circling the giant planet, much to NASA's surprise. It also discovered 2 new moons, Thebe and Metis. Furthermore, Voyager 1 returned stunning detailed images of Jupiter's major Galilean moons, Io, Europa, Ganymede, and Callisto, as well as Amalthea. The Voyager spacecraft, like the Pioneer spacecraft before it, discovered Jupiter's moons to be active worlds in their own right, and Voyager 1 discovered some fascinating facts about these natural satellites. Io's numerous volcanoes and mottled yellow-brown orange surface, for example, demonstrated that moons, like planets, can have active interiors. Furthermore, Voyager 1 returned images of Europa that showed a relatively smooth surface broken up by lines, implying ice and possibly an ocean beneath. Subsequent observations and analyses have revealed that Europa most likely contains a massive subsurface ocean of liquid water capable of supporting Earth-like life. In March 1979, Voyager 1 made its closest approach to Jupiter, coming within 174,000 miles or 280,000 kilometers of the turbulent cloud tops. The probe was then directed towards Saturn. Close-up images of Saturn were available about a year later, until 1980, and the ringed planet, like Jupiter, proved to be full of surprises. The F-ring, a thin structure discovered only a year before by NASA's Pioneer 11 probe, was one of Voyager 1's targets. Prometheus and Pandora, 2 new moons discovered by Voyager's higher-resolution camera, keep the icy material in the F-ring in a defined orbit. It also discovered Atlas and the G-ring, as well as images of several other of Saturn's moons. One puzzle for astronomers was Titan, the second largest moon in the solar system after Jupiter's Ganymede. Titan's close-up images revealed nothing but an orange haze, fueling years of speculation about what lay beneath. It wasn't until the mid-2000s that humanity discovered this, thanks to images captured from beneath the haze by the European Space Agency's Huygens atmospheric probe. The encounter with Saturn signaled the end of Voyager 1's primary mission, but the probe wasn't ready for retirement yet. The focus simply shifted to tracking the 1,590-pound craft as it raced toward interstellar space. However, 2 decades before that, Voyager 1 captured one of the most iconic images in spaceflight history. In February 1990, the probe turned to face Earth and captured an image of its home planet from 3.7 billion miles, or 6 billion kilometers away. At that massive distance, the Earth appears as a tiny dot suspended in a ray of sunlight in the photograph. That same day, Voyager 1 took dozens of additional photos, including 5 other planets and the Sun, in a multi-image solar system family portrait. The pale blue dot image, on the other hand, stands out, reminding us that Earth is a tiny outpost of life in an incomprehensibly vast universe. In August 2012, Voyager 1 broke free from the heliosphere, the giant bubble of charged particles that the Sun blows around itself. The discovery was made public the following year in a study published in the journal Science. The findings were discovered after Voyager 1's plasma wave instrument recorded a powerful solar eruption between April 9th and May 22, 2013. Electrons near Voyager 1 vibrated as a result of the eruption. Researchers discovered from the oscillations that Voyager 1's surroundings had a higher density than what was found just inside the heliosphere. Now, it may appear contradictory that electron density is higher in interstellar space than in the vicinity of the Sun. However, researchers explain that the electron density at the heliosphere's edge is significantly lower than at Earth's surface. Researchers then went back through Voyager 1 data and determined the official departure date to be August 25, 2012. The date was determined not only by electron oscillations, but also by measurements of charged solar particles taken by the spacecraft. On that fateful day, the same day that famed Apollo 11 astronaut Neil Armstrong died, the probe detected a 1,000-fold decrease in these particles and a 9% increase in galactic cosmic rays, which originate outside the solar system. Voyager 1 was 11.25 billion miles, or 18.11 billion kilometers from the Sun at the time, or about 121 astronomical units (AUs). NASA's Planetary Science Division explores the solar system in the following manner: flyby, orbit, land, rove, and return samples. The Voyagers were and continue to be the scouting party and the architects of this paradigm. They paved the way for us to take the next steps with flybys. The Voyager spacecraft enabled us to survey the universe and determine our research priorities. The Voyager flyby missions reinforce the planetary science paradigm, which has been and continues to be enormously successful. The principle of gravity assist, using the mass of a planet or another object in space to change the speed and trajectory of a spacecraft, was critical to the success of the Voyager's tours of the outer planets. Voyager 2 used gravity to travel to Jupiter, Saturn, Uranus, and Neptune. In that way, the Voyagers walked so that other probes could fly. Since then, a number of missions have used gravity assist to save fuel and significantly shorten the time it takes to reach destinations in the outer solar system. For example, New Horizons flew by Pluto propelled by Jupiter's gravity. OSIRIS-REx, on its way to asteroid 101955 Bennu, received a gravity assist from Earth, allowing it to reach its destination faster. Messenger mission planners, on the other hand, used gravity assist in slowing the spacecraft down so it could successfully enter Mercury's orbit. Messenger was assisted by Earth, Venus, and Mercury itself 3 times before being placed in Mercury's orbit. En route to Saturn, Cassini received 2 gravity assists from Venus and 1 each from Earth and Jupiter. Cassini has mastered the art of gravity assists and is constantly reshaping Saturn's largest moon, Titan, with close flybys. This has provided Cassini with new views of many Saturnian moons that would otherwise be inaccessible, as well as significant scientific results. Another mark the Voyagers have left on space exploration is memory management. While the Voyagers had limited programmable memory, it proved to be a valuable resource that was frequently used and reprogrammed. As a result, all subsequent planetary missions were outfitted with large programmable memories. In addition, the Voyagers established the course for future planetary exploration. Though they taught us a lot about the ice giants and their moons, the relatively primitive instruments and low volume of data returned raised more questions than answers. It was really a case of the more we learn, the more we appreciate what we still need to learn. As a result, Voyager paved the way for a number of NASA missions, including the Galileo and Juno missions to Jupiter, as well as the Cassini mission to Saturn, which received gravity assistance from Jupiter. And now Voyager 1 has revealed a lot about the part of the solar system called the edge of the Sun. Our solar system is nestled within the Milky Way galaxy, home to more than 100 billion stars. The solar system is surrounded by a bubble known as the heliosphere, which protects us from the vast galaxy beyond as well as some of its harsh space radiation, else we would have been toast. The heliosphere thankfully shields us from that radiation, which is created by another source of radiation, the Sun. The Sun constantly spews charged particles from its surface, known as solar wind. The magnetic field from the Sun is carried by the solar wind, which flies out to about 4 times the distance of Neptune. The heliosphere was discovered in the late 1950s, and many mysteries surround it. Scientists are learning more about how the heliosphere protects astronauts and spacecraft from radiation, and more broadly, how stars can influence their neighboring planets. Meanwhile, radiation is not always bad. When you sunbathe, you are soaking up the sun's rays. Radiation is what warms the leftovers in your microwaves and is used in medical imaging. However, space radiation is more similar to the radiation emitted by radioactive elements such as uranium. Galactic cosmic radiation, or GCR, refers to space radiation emitted by other stars. Supernovae, black holes, and neutron stars are examples of active areas in the galaxy that can strip electrons from atoms and accelerate nuclei to nearly the speed of light, resulting in GCR. On Earth, we are blessed with 3 layers of protection from space radiation. The first is the heliosphere, which helps to keep GCR from reaching the solar system's major planets. In addition, the Earth's magnetic field generates a shield known as the magnetosphere, which keeps GCR away from Earth and low-orbiting satellites, such as the International Space Station. Finally, the gases that make up Earth's atmosphere absorb radiation. When astronauts travel to the Moon or Mars, they will not be protected in the same way that we are. They'll only have the heliosphere to protect them, which varies in size over the Sun's 11-year cycle. The Sun goes through periods of intense activity and powerful solar winds during each solar cycle, as well as quieter periods. When the wind dies down, the heliosphere deflates much like a balloon. The heliosphere then expands as it picks up speed. The heliosphere consists of 4 main parts. The major planets of our solar system are all located in the heliosphere's innermost layer. Here, the solar wind travels at full speed, about 1 million miles per hour for billions of miles, unaffected by galaxy pressure. The termination shock is the outer boundary of this core layer. There is also the heliosheath located beyond the termination shock. As it encounters the pressure of the interstellar medium outside, the solar wind moves more slowly and deflects in this part. The third is the heliopause, the sharp final plasma boundary that separates the Sun from the rest of the galaxy. The magnetic fields of the solar and interstellar winds collide here, and the inside and outside pressures are balanced. The last is the outer heliosheath, the region just beyond the heliopause that is still influenced by the presence of the heliosphere. Voyager 1 worked with the Interstellar Boundary Explorer, or IBEX, to study the heliosphere. IBEX is a 176-pound suitcase-sized satellite launched by NASA in 2008. IBEX has been orbiting Earth since then, equipped with telescopes to observe the heliosphere's outer boundary. IBEX detects and analyzes energetic neutral atoms, or ENAs, that pass through its path. ENAs form when the interstellar medium and solar wind collide. Some of these ENAs return to the solar system's center and IBEX. So whenever you collect one of those ENAs, you know where it came from. By collecting a large number of those individual atoms, you can create an inside-out image of our heliosphere. Furthermore, scientists discovered that the heliopause changed dramatically in a very short period of time after reviewing data from Voyager 1 and Voyager 2. That explains why there was such a large gap between the two probes' entrances into interstellar space in 2012 and 2018 respectively. Voyager 1 also detected a strange hum coming from outside the solar system, which we would never have detected without the spacecraft. Stella Koch-Ocker, a Cornell University doctoral student in astronomy, discovered the sound in data from Voyager's plasma wave system PWS, which measures electron density. Ocker and her colleagues described the drone produced by plasma shock waves as very faint and monotone, owing to the frequency's narrow bandwidth. While the researchers believe the persistent background hum is caused by interstellar gas, they don't yet know for sure what is causing it. It is possible that it's caused by thermally excited plasma oscillations or quasi-thermal noise. The study also suggests that this is not the last we'll hear of the strange noise. The persistence of the emission suggests that Voyager 1 may be able to continue tracking the interstellar plasma density in the absence of shock-generated plasma oscillation events. The droning sound the researchers believe may hold clues to how interstellar space and the heliopause interact. The PWS instrument detected disturbances in the gas caused by the Sun when it first entered interstellar space, but it was between such eruptions that the researchers noticed the steady signature of the near vacuum. Senior author James Cordes, an astronomy professor at Cornell, compared the interstellar medium to quiet or gentle rain, adding that detecting a solar outburst is like detecting a lightning burst in a thunderstorm, and then it's back to the quiet or gentle rain. However, as faithful as the Voyager 1 has been, it has begun giving its handlers something to worry about. NASA has confirmed that Voyager 1 has been sending back mysterious data. The probe's Attitude Articulation and Control System, or AACS, is in charge of controlling the spacecraft's orientation, pointing its high-gain antenna toward Earth and controlling attitude maneuvers. The AACS has now returned data that contradicts what is happening aboard Voyager. According to the space agency, the Interstellar Explorer is functioning normally, receiving and executing commands from Earth as well as gathering and returning science data. However, AACS readouts from the probe do not accurately reflect what is happening on board. All indications indicate that the AACS is still operational, but the telemetry data it is returning is invalid. For example, the data may appear to be generated at random or may not reflect any possible state of the AACS. The problem hasn't triggered any onboard fault protection systems which are meant to put the spacecraft into safe mode, a state in which only essential operations are performed, giving engineers time to diagnose a problem. The signal from Voyager 1 hasn't weakened either, indicating that the high-gain antenna is still pointing in the right direction toward the Earth. NASA said the team would continue to closely monitor the signal in order to determine whether the invalid data is coming directly from the AACS or from another system involved in the production and transmission of telemetry data. However, the team at the time could not predict how long the spacecraft would be able to collect and transmit scientific data until the nature of the problem was better understood. However, Suzanne Dodd, project manager for Voyager 1 and 2, explained that this was not totally unexpected. At this stage of the Voyager mission, a mystery like this is sort of par for the course. The spacecraft are both nearly 45 years old, which is much older than the mission planners anticipated. They're also in interstellar space, a high-radiation environment in which no spacecraft has ever flown. As a result, the engineering team faces some significant challenges, but she believed the team would find a solution to this problem with the AACS. If they do find the source, they may be able to solve the problem with software changes or by utilizing one of the spacecraft's redundant hardware systems. Of course, Voyager 1 has previously encountered difficulties. The spacecraft's primary thrusters were showing signs of wear and tear in 2017, so on Voyager 1, engineers used thrusters that had previously been used during the mission's planetary encounters 37 years before. However, NASA engineers have been able to locate the problem with Voyager 1. The AACS began sending telemetry data through an onboard computer known to have failed years ago, and the computer corrupted that data. The project manager suspected this was the problem and chose a low-risk solution, commanding the AACS to resume sending data to the correct computer. Engineers aren't sure why the AACS began routing telemetry data to the wrong computer, but it was most likely caused by a faulty command generated by another onboard computer. If that's the case, it means there's a problem somewhere else on the spacecraft. The team will continue to look for the underlying problem, but they do not believe it poses a threat to Voyager's long-term health. Voyager 1, however, will have to come to an end one day. In fact, time is running out. The spacecraft is powered by nuclear batteries that generate electricity from the heat produced by plutonium decay. Every year it produces 4 watts of heat less. NASA has been shutting down redundant systems. The team only operates the instruments that can take data where the spacecraft are. For instance, the camera is no longer operational because it's very dark where they are and there is nothing to see. And some of the power is used to keep heaters running to keep the spacecraft's instruments from freezing. Let's hear what you think about the Voyager mission in the comments section below.